Good afternoon, everyone. Welcome to the session 2 of day 2. Eminent speaker of this session is Professor Dr. Amitava Chatterjee from Jadavpur University, Electrical Engineering Department. I would like to request Professor Dr. Chandan Chatterjee, Chandan Chatterjee, to felicitate our speaker with the memento. Kindly. I am feeling really fortunate to introduce Professor Dr. Amitava Chatterjee before you. He is one of my teachers in jail, so really I am feeling lucky to introduce him to you. I am reading before you his brief biography. Amitava Chatterjee, Dr. Amitava Chatterjee received his BEE, MEE and PhD degrees in electrical engineering from Jadavpur University, Kolkata in the year 1991, 1994 and 2002 respectively. In 1997, he joined the Department of Electrical Engineering in Jadavpur University. He is a recipient of the Jadavpur as a faculty where he is currently serving as professor. He is a recipient of the Japanese government scholarship in 2003 and a recipient of the Japan Society for the Promotion of Science (JSPS) postdoctoral fellowship in 2004. In 2004 and in 2009, he visited University of Paris 12, XIA, Vallée-Marne, France, and in 2017 he visited University of Paris, PhD, as an invited teacher. Dr. Chatterjee became a fellow of Indian National Academy of Engineering (FNAE) in 2018. He is a fellow of IETE India, a fellow of the Institution of Engineers India, and a senior member of the IEEE USA, and a life member of Operational Research Society of India. Dr. Chatterjee's key research interests include systems and controls, signal and image processing, AI and ML, intelligent instrumentation, and robotics. Dr. Chatterjee has co-authored 2 books and co-edited 2 books, all published by Springer Publishing. In the past has served in the past as an associate editor-in-chief of IEEE Transactions on Instrumentation and Measurement, and editor of IEEE Transaction on Vehicular Technology and Engineering Applications of Artificial Intelligence Journal Elsevier, and associate editor of IEEE Sensor Journal, IEEE Open Journal of Instrumentation and Measurement, ISA Transaction Journal Elsevier, and Control Engineering Practice Journal Elsevier, and as an editorial board member of Artificial Life and Robotics Journal Springer. He has authored or co-authored more than 190 from Stanford University in 2020, 21, 22 and 23, 4 consecutive years. both in lifelong career category and in single year category in each year. So, with this, I would like to welcome Professor Dr. Amitava Chatterjee for his speech. Sir, kindly the stage is yours now.
First of all, I would like to thank the organizers of this ATAL-FDP and the administration of Physical Engineering College, Mechanical Engineering Department faculties associated with this college, and Professor Chandan Chatterjee, who is the HOD of this department. And especially I would like to thank Dr. Abhijit Banerjee for inviting me to deliver this lecture. So I guess that many of you are from a broad spectrum of different branches of engineering who are rather present here to go through that presentation that I have to make today. So the topic that I shall be discussing is essentially called that computer vision based gesture recognition in collaborative robotics. I'm not sure what are the other topics that will be covered as a part of this particular FDP. Sorry. One thing I can say appeals to me, because probably many of the speakers are essentially from the mechanical background. So they will be essentially speaking on many topics which are essentially more from the mechanical perspective. Probably, I'm not sure. Probably that's the case. My presentation will be a little different. My presentation will touch upon the other aspect of robotics, which is more in the context of the intelligence part. So essentially, we will talk about something which is in the context of, we might say, the computer science, electronics, electrical merged with mechanical. So that probably will give you a true feeling of what mechatronics is all about. Because mechatronics means that it's basically a purely interdisciplinary domain where there are contributions from many different fields, all from mechanical, electrical, electronics, computer science, instrumentation. Everybody has to make, or everybody has a scope to make some contribution in that field. So from there, my topic of discussion will essentially be concentrating on something which is related to the intelligence part that we can have in the context of robots. So in that sense, these are some standard disclaimers that every time I put forward, so that everybody is comfortable about the disclaimers, and you can go through the standard disclaimers. I don't have to read it out, but these are all the standard disclaimers I every time put in. So let me now come to the main topic of discussion in today's lecture. So essentially what I shall be discussing is about collaborative robotics. Now, collaborative robotics, those who are associated with robotics, they are more or less conversant with the term. So let us first discuss why collaborative robotics has become so important in recent days. Although the origin of robotics, it appeared to be from the very beginning of the early part of the 19th century. But effectively, robotics came into prominence in the last 40 years, 30 to 40 years essentially. So maybe about 30 years back or 40 years back, when it was gradually developing into a very mature, very prominent field, then people had an idea that a robot can do anything and everything. If you look at the movies in Western world, Terminators, cyborgs, those were the kind of movies where you can see that the robots can do anything and everything, and they can always surpass a human being. But movies are movies, after all. So essentially, very soon people started realizing that even emulating the capability of a 3-year-old child, the brain of a 3-year-old child, the 4-year-old child, is a hell of a difficult job. So gradually the expectations from robotics got lower and lower over a period of time. Initially, it was like a robot can do everything on its own. So there came the importance of autonomous robots working in autonomous mode. But when the robots work in autonomous mode, then people found that the scope of application where they can meaningfully carry out job was getting narrower and narrower. Gradually, people started realizing that probably if we have a robot rather doing the entire thing on its own, if they collaborate with a human being, probably the scope of application will become wider and wider. So then the concept of collaborative robotics came, and probably in the last decade, in last 10 years, you will see that human-robot collaboration, human-robot interaction, collaborative robotics, these terms are getting so much important. So the idea is that in most situations what people feel is that, say for example, many of you are from the mechanical background maybe. Let me take an example of a manufacturing line, a conveyor belt. There are people have, I think many of you have seen the film Modern Times of Charlie Chaplin, where there were workers who were basically working like robots. So, like say for example, two people who are working in a assembly line, in a conveyor belt kind of situation, maybe two people will work in synchronism, where some of them, one person will deliver some object to the other person, and accordingly the work will go on. Now, any human being carrying out that work is bound to get fatigued over a period of time. His or her performance is going to get diminished over a period of time. If you employ in that particular day in day out job a robot will not get tired. You can use a robot for a precise repetitive job for many hours without getting tired, without getting jeopardized its performance. Without jeopardizing its performance. So a day-to-day regular work can be very well done by a robot, perhaps in place of a human being. But every now and then, in every industrial application, at some point of time, there will be a situation where you will need some intricate brain operation, some complicated decision making to be carried out. For such kind of decision making to be carried out, it is always better if a human being carries out that decision making rather than a robot. It's been established till now, no robot till now has not yet been found to be that effective that it can completely replace a human being. So that's where the collaboration or unison of robot and human being has become or has come in prominence. That day-to-day regular kind of job robot can do well, whereas complicated decision making, complicated jobs can be done better by a human being. So there is the way they can communicate with each other. Then there will be more varieties of problem in real life that can be solved by using a robot and a human being together in collaborative mode. And if you look at, I do not know, probably Professor Homing is going to talk tomorrow. He will probably going to talk about Industry 4.0, 5.0, 6.0. You will find that Industry 4.0, there the basic concept was probably till that point of time that the robot was a competitor of a human being. As if the robot is going to replace a human being. And in developing countries like ours, that's not really a very good scenario. But the situation is gradually changing now. In Industry 5.0 perspective, it is human and the robot, they are more of collaborator than competitor. So collaborative robotics, as I see, is going to gain more and more prominence in next 2-3 decades if not. So then what is the basic way of implementing a human and a robot in an industrial scenario? Generally, say for example, we human beings, we gather information about the surroundings using our sensory organs, isn't it? Robots have sensors who have to gather information about the surroundings, isn't it? So some information that they gather about the surroundings, after gathering that information, the robotic system, after gathering that information through the sensors, They intelligently process that information and then they actuate. Say for example, if we feel that it's too cold now, I will probably put on a jumper. So if I feel that it's too cold now, that means my sensory organ is sensing that the temperature is a little low. And the putting on a jumper is like some actuation being carried out. Robots do the same way. There is some way of sensing and some way of actuating some output. We know that the sensors have some, say for example, some mechanical input and the output is electrical, and actuators the other thing. The input is electrical, output is mechanical. But in between, you have that learning methods and the collaborative strategies. These are the two new blocks that are getting introduced, out of which learning methods were already there, you can say, in the robots. But the collaborative strategies is a new block exclusively for the collaborative robotics domain. In an original autonomous mode of robot, such collaborative strategies block will not be present there. So if you look at the sensors and actuators, there are a varieties of sensors and actuators associated with the robot. There can be, for example, vision-based sensor, robotic skin-based sensors, tactile sensors. Similarly, actuators can be like electric motors or pneumatic ones, or if you want heavy-duty application, there can be like electric motors and hydraulic motors, for example. So electric motors are basically for the small applications, very fast applications, and hydraulics are, I think everybody can hear me. Yes, okay. Yes. And the hydraulics are essentially for the very heavy-duty applications. But this itself can be a topic of another lecture itself. I am not going to concentrate on that today, because today I am going to concentrate on gesture recognition, gesture-based collaborative robotics. So let me move on. What I am going to discuss here, probably I have 4 or 5 different applications of how gesture can be utilized for collaborative robotics. I think it's okay. I think, am I audible from the last bit? This is okay, sir? Okay, fine. So as I was mentioning, I will consider 4 or 5 typical research problems which can be equally of industrial prominence, and I will try to show how those problems have been solved. Some of those are developed at different corners of the world. Couple of those are developed in our laboratories and try to make a judicious mixing of both kind of activities. The first one I will discuss about is called gesture-based human-robot handover. I am assuming, say for example, as I mentioned, as I gave that example, that in an industry line, in an assembly line, there is one robot and there is one human being. And some object has to be transferred between the robot and the human being. How that can be done in a seamless fashion? That is the problem of interest here. So, to understand or to show, to make the robot know that I want to give some object to the robot, or I want to capture some object from the robot, there has to be some gesture shown or gesture made. So showing that gesture can be done in 2 ways. Either I can utilize computer vision, that means I can use a camera for showing the gesture, and the another way can be in the domain of wearable robotics. What is wearable robotics? You have some sensors which you wear. Those sensors capture some information based on the gesture shown, and it is the responsibility of the robot to decipher what is the exact gesture being shown to that particular human being. So essentially for this particular problem, I shall consider the physical contact based approach, not vision based approach, because our words are essentially vision based, which I shall come to it later. So this is the basic, I hope you can read the title. The title says human robot handover. This is the basic scheme, complete scheme. So if you look at the scheme, this is the volunteer. The volunteer, I hope you can see here, can you see that there is a black arm band here? the black armband contains the sensors. I think he is wearing it in the left hand. So there is likewise this watch. So there is a black band. In that black band, there are some sensors. I am coming to those descriptions of those sensors. So this is the black band, and the human is at this moment, if human is basically holding an object. So if the human is holding an object, it's like it is trying to tell the robot that robot, I want to give the object to you, like that. One particular example. So when this handover intention, that is he or she is holding this object, somehow that intention has to be conveyed to the robot. The robot has to understand that I am trying to give it the object. How it can be done, again in next slide I come to it. Somehow let us assume that some sensory data is captured in the data layer, that the data acquisition has taken place. When data acquisition in some raw form, that means sensory data has been acquired in raw form, some mathematical manipulation on that, not manipulation sometimes appears in a very, what shall I say, degraded way. It means some intelligent processing of it has been carried out, such that data is properly extracted for meaningful use. And because there are more than one type of sensors, as you can see, there is a black band, and the black band contains more than one type of sensor. So why more than one type of sensor? Again, next slide. But when there are more than one type of sensor, basically more than one type of information you are gathering. When more than one type of information you are gathering, then you have to assimilate all of them together. Means there has to be some fusion carried out. So that is known as some data fusion. The data fusion is basically here based on some sensory data. So you can also call it sensor fusion. The sensor fusion will create an augmentation of all these data. When all this data augmentation has been carried out, that means the data layer, its objective is over. Once the data layer has been executed, all data have been accumulated in a meaningful fashion, then from there a meaningful decision has to be taken. Meaningful conclusion has to be drawn. For drawing the meaningful conclusion, there is a decision layer. So what is the objective of the decision layer? The decision layer, based on the sensory data that I have created in the data layer, it has to identify that whether the human being is trying to give me the object or whether the human being is asking an object from me. So that particular human intention recognition has to be carried out. When the human intention is correctly recognized, then some action planning algorithm will come into play. The third block I will talk about later. Now somehow let us assume that the robot has specified that the human is trying to give me the object. I am the human being. I am standing in front of this robot and I am showing the object. Robot has understood that it has to take the object. But how? It has to somehow come to the object and grab it, isn't it? So how that can be done? Grabbing the object, that can be carried out by using an end effector, isn't it? The robot has an end effector. The end effector is like my fingers, they can come and grab the object. To grab the object, the robot has to know where this object is and where the robot is. So that will come under the purview of the execution layer. So execution layer, what does it have? What are the current states? Current states means where the robot is actually. What are the goal states? What does that mean? Where is the object? And there has to be a precise control algorithm has to be written such that the end effector from here comes and picks up this object and places it wherever it is designed to place. So there are three basic building blocks in this entire world. First, some data acquisition, assimilation of the data in a very meaningful form. Second, from the assimilated data, you actually make some decision, meaningful decision out of it, whether to take the object, whether to give an object. Once that decision is known, that what has to be carried out, the next point is how to carry it out physically. To carry it out physically, implement it physically, you have the execution. So that is how this entire
communication will take place where this particular robot and this end effector has to take the object from here and maybe place on a table or somewhere else. That we'll see. That is the basic objective. You can always interrupt me during my presentation at any point of time. And you can ask me questions umpteen number of times. I shall try to explain to the best of my ability. Okay. So now, this is the complete scheme. Complete scheme in the sense, first layer of the complete scheme. What was the first layer? The first layer was assimilating data. How the assimilation of data can be carried out? I hope you remember that a human is wearing a black band. Why is the human wearing a black band? The human is wearing a black band because in that black band there are two varieties of sensors. One, IMU. What is the full form of IMU? Inertial measurement unit. Why inertial measurement unit? Why this sensor is used? This sensor is used for finding out the orientation of any body, any rigid body, any particular element. Why it is used here? Say for example, for showing any object or asking for an object from the robot, I have to move my hand, isn't it? Essentially, I have to move my forearm. So for forearm movement, that angular orientation of my forearm, that will be captured by this IMU that is being present here. Can you see the IMU? The forearm rotations will be computed from that IMU. Along with the IMU, there are also in this particular black band, there are 8 EMG sensors. Anybody knows what is the full form of EMG? What is the full form of ECG? Electromyogram. So ECG is electrocardiogram, electroencephalogram, EEG, and EMG is electromyogram. So what is electromyogram? Electromyogram, these sensors, if there is some muscle activities in a human muscle, then EMG sensors will convert that to an electrical potential. How it is utilized here? In that black band, 8 EMG sensors are there at an angular separation of 45 degree. 8 into 45 degree makes it 360 degree. 8 EMG sensors are there. Why they are here? Whenever you are grabbing an object or asking for an object, not only the forearm movement is important, your finger movement is also important. So this kind of an information that this gives me the object and I want to give the object, there are two different ways the fingers are being placed. That finger movement difference can be conveyed or can be acquired if I have EMG sensors, because muscles are moving. From those movement of the muscles, I can capture corresponding electrical signals. So EMGs are essentially 8 EMGs are there, EMG sensors are there in that black band, and they are essentially for calculating the finger motions. Now just remember, just consider, say for example there is some finger motion. Say if I have my fingers like that, if I don't move my fingers, what do you feel? That EMG sensor output, how does it look like? It will be a constant value, isn't it? Say for example, under normal circumstances, these EP, finger motion signals versus time, is a signal like that. If I do not move my fingers, what will happen? Basically, this will be a constant. If I move my fingers, depending on different varieties of movement, the signal variety will be different. If I move my fingers slowly and if I move my fingers rapidly, what will be the difference? The signal will vary rapidly if I move my fingers rapidly, and the signal variation will be slow if I move my fingers slowly, isn't it? So, whether you have moved your your fingers rapidly or you have moved your finger slowly, that can be calculated or that can be understood by comparing or by calculating standard deviation of this signal. Do you understand? The standard deviation represents what? Some variation in the signal, isn't it? If I calculate the mean will not reflect that. A standard deviation will reflect whether the fingers were moved very frequently, very dynamically, or in a very slow manner. To speak grossly, to make the concept understood in a very gross manner. Okay, so this is how you can say then that essentially I have 8 EMG sensors. For 8 EMG sensors, I have 8 EMG signals of electrical signals as output, like ET versus T. You all will understand that in any case, the signals are not acquired in continuous domain, but in discrete form. So essentially, the signals will come essentially like discrete form, like this, isn't it? And this will be some discrete signal, not continuous, but continuous concept I drew to make you understand how the actual situation is, to make the spirit understood. Then from that finger motion and from that forearm rotation, there are now two different varieties of sensors. I can fuse that information. When I fuse that information means I accumulate the total information that is the part of this data fusion. So how mathematically the data fusion is carried out? This is the mathematical part that will be carried out in reality. I am standing in front of the robot. Let me assume that this is the robot. Somehow I have moved my hand like that with some finger connection. Now in that situation, look at this. I have some EMG sensors and I have an IMU. The IMU essentially is a 9-axis IMU. Okay, there can be different axis varieties. Most importantly, these IMUs can calculate what is the angular velocity and what are the angular accelerations. From there, mechanical people will be able to associate it more clearly. There is something called quaternion. Quaternions can be calculated from those. Quaternions from this IMU sensor, you will get these X, Y, Z, these three quantities. From the IMU sensors, you will get this X, Y, Z values. And quaternion means you have to calculate a fourth quantity. The fourth quantity is called the scalar W, such that this is the relation to be followed, respected. So if my IMU sensor gives me these quantities X, Y and Z, then I can calculate the square of that, and 1 minus this entire thing will give me W square, so W will be root over of that. So what does that mean? That if my IMU sensor gives me X, Y, Z, in a way you can say it also gives me W. So these four quantities can be calculated for each specific forearm rotation, isn't it? Secondly, that is for the IMU only. Apart from IMU, what are the other sensors present there? EMG sensor. Why is there EMG sensor? EMG sensor is for capturing the finger movement. IMU is only for forearm rotation. So for finger movement, what you can do, I am coming to that. But IMU part is still not over. Why? Again, mechanical people will tell you better. They understand this part better than electrical, electronics, computer science people. I mean, those who have read everything, that's fine. But generally, basically because they are taught these parts as part of their course, that quaternions are rather a little bit abstract thing that people try to find difficult in visualizing. What they can visualize better, why it is, what are we trying to do? When we are moving the forearm, what is the angular rotation in a particular axis scheme? In the physical world, in the actual scheme, what are the angular rotation? An angular rotation in X, in Y and Z. So those angles we all know are known as Euler angles. People can physically associate with Euler angles better than quaternion, most people. So if you have quaternions, from the quaternions the Euler angles can be calculated. What are these Euler angles? Everybody who is working in robotics, they know that. This is roll, pitch, yaw, isn't it? These are the three main quantities that everybody knows in robotics. So roll, pitch, yaw are like three angles. One angle like this, another angle like this, another angle like this. So these three angles are given by, say for example, phi, theta and psi. Roll, pitch, yaw. So phi is the roll rotation, theta is the yaw rotation, and psi is the pitch rotation. And they can be calculated from this equation. Look at this. You originally had a vector q. How many quantities were present in vector q? 4 quantities. W, x, y, z. That was, you can say that is a 4 by 1 vector. That 4 by 1 vector now gets modified to a 3 by 1 vector. Why 3 by 1 vector? 3 quantities. What are those? Roll, pitch, yaw, phi, theta, psi. Look at the expression of phi, theta, psi. Tan inverse, sin inverse, tan inverse. Inside everything is comprising W, X, Y, Z. So if I have that quaternion, I can directly calculate phi, theta, psi, isn't it? Every other quantity on the right hand side is known. So I can calculate what is the value of phi, theta, psi. Phi, theta, psi. So from the IMU sensors, we first calculated quaternions. From the quaternions, we calculated Euler angles, and those Euler angles gave us roll, pitch, yaw rotation or angles. From IMU, second set of sensors.
From IMU, we saw that x, y, z. What about x, y, z? Acceleration or angular acceleration?
Angular acceleration. Angular comprising angular, they will give you angular velocities and angular acceleration. From the linear theta, I think you cannot calculate this phi theta psi, isn't it? Those are angular accelerations. Angular velocities, angular accelerations, not linear. So from there, phi theta psi, 3 quantities are known. Now there are 8 EMG sensors, isn't it? From 8 EMG sensors, I have moved my hand like that. At the same time, by moving this hand like that, I may have shown that give me the object, or I have shown that I want to give you the object. So some finger movement is there. As I make, actually that is in the left hand, and I am myself a left-hander actually. So it's easier for me. So if I move my fingers like that or like that, what will happen? Some muscle movement will be present. That muscle movement for specific EMG sensors, different EMG sensors will be activated in a different manner depending on my finger movement. So for any specific finger movement, you can understand how many EMG signals will I gather? 8. E1 to E8. I have shown you E1, ET. 8 EMG sensors, E1 to E8. E1 versus time to E8 versus time, for example. In discrete manner, the data is being captured. But that data is like something like this. I told you that we don't take entire data. What do? You calculate the standard deviation. If the standard deviation becomes 0 or a constant value, that means I am not moving my fingers at all, like that. So you have in the data fusion block, the data fusion block does what? That it creates a vector of dimension 11 by 1. Can anybody tell me why it is 11 by 1? Because from the IMU sensor, I have 3 quantities, phi, theta, psi. And then from 8 EMG sensors, I have 8 signals. For each one of those signals, I calculated the standard deviation. So standard deviation of E1, standard deviation of E2 up to standard deviation of E8. It comprises 1. So every time in this system, whenever you are wearing the sensors and you are showing some gesture, it is getting converted to a 11 by 1 vector. Now simply remember that you and I and everybody present here, we are all volunteers. And we are asked that carry out 10 or 6 specific gestures 100 times. So what will happen? For each one of us, 10 gestures 100 times means 1000 data will be gathered, isn't it? And 1000 means what? 1000, every one of a dimension of 11. Are you getting my point? Say for example, there are 10 gestures. I am asked that you carry out each gesture 100 times. That means you show this hand 100 times. What will happen? For each time I show the hand, the robot will capture what? Some data, all this information, it will get converted to what? 11 by 1 vector. 1 vector for 1 gesture. Now 1 gesture, 10 gesture. How many such vectors? 10 vectors. 100 times is what? 1000. 10 into 100 is 1000. And every time the vector size is how much? 11 by 1. Which means that I create a matrix of dimension 11 by 1000 for 10 gestures. Could I make myself understood? So that is how the entire data, those who are conversant with neural networks, deep learning, or for example, everybody these days people they can directly associate with deep learning. So deep learning means what? Some kind of training data. You can say this is the training data. You and me and everybody, we are the volunteers. We show the gestures, system understand that this 11 by 1 vector is like that. It means that this guy is asking for an object. Now what are these intentions? I told you there are two gross intentions. What are those? That you either give the object or you take the object. So that can be like, I need the object from you and I want to deliver the object from you. This problem is rather too simple. How many gestures? 2 gestures. Only 2. So the problem is not that simple. They made the problem a little more complicated. What was a little more complicated scenario? They subdivided the situation into 6 intentions. What are the 6 intentions? We need the object. We want to give the object. Robot, you stop. That means robot, you don't move. Robot, you continue. Robot, you can speed up your movement. Robot, you can slow down your movement. So there are 6 intentions. For each intention, me being a volunteer, I am asked that sir, please you go and you show that need. Every time I show like that. Sir, you do that 100 times. 100 signals are across. 100 signals mean what? 11 by 1 vector, 11 by 100. 11 by 1 is for one such signal and 11 by 100 means 100 such vectors, isn't it? Like that. So, the next question is, you tell me that sir you go and show the robot that you need the object. So I will come and I will show that sir, I need the object, please give it to me. Then you will come and your gesture is like that. Somebody else comes, shows like that. It's very difficult to make the robot so intelligent so that the robot can understand that all are needing the object. So there has to be a standardization. There has to be a standard protocol. The volunteers have to know that okay, if I show my hand like that, then it means that I am needing the object. So look at these gestures. Can you see that everybody was asked to carry out, every volunteer was asked that if you want to need the object, show it like that. Need, give, robot you stop, continue. And they, of course, slow down and speed up is very difficult to naturally gesture it. So they showed that one is for slow down, another one is for speeding. So everybody had to show, all volunteers had to show these expressions. And along with that, in that process, the all training data was captured. So what is the objective of the training data? You can develop your robot intelligent module based on that training data. When the system is trained using that, then a new unknown gesture is being shown to the robot can now decipher what kind of gesture it is. That is the basic idea. Okay? But problem is not that simple. Okay, what is this? Say for example, I am standing in front of the robot. By mistake. Somehow, say for example, a friend of mine is coming. So I'm asking him, please come. Robot will already capture that signal, and it will understand that I am asking an object from the robot, isn't it? So it means there can be a false triggering of the robot in the process of the experimentation. How can I take care of that? I can take care of that by the situation where I tell the robot explicitly when the data acquisition should start. What is meant by that? You have seen Western classical symphonies. The conductor, every time the Western classical symphony starts, they start like that, isn't it? Then the music starts, then the cello start playing, then the violin start playing, viola start playing like that. So they developed a protocol like this. Every time you make 4 such gestures. For each gesture, again that 11 by 1 vector will be captured. So a series of 4 such 11 by 1 vector captured will signal the robot, now I can capture the data. That means now the data acquisition has started. Before that, whatever gesture you show to the robot will stand still, it will not capture it. Robot will only capture the data when such a specific protocol. Again, you can develop your own protocol. It does not mean that everybody has to do this protocol only. But in any situation, the thing is that there has to be certain standardization. They have proposed something and they have proposed keeping the real world in mind. In the real world, if you understand, this is how, like any musical show, it starts like that. Why? Because unless and until the conductor shows that hand, 100 cellos cannot synchronize with each other. They can start at any time playing. To make that synchronization, they need their hand gesture. So they mimic that hand gesture of that Western classical conductor in their robot experiments. So once that is done, is there any question up to this point? Is understood? Now see, entire database of signals have been captured. Many signals. Say for example, as I mentioned, that there may be there are 6 intentions. Maybe there are 100 such training data for each intention. So there are more 600 intentions. For each intention, there is 11 by 1 vector. So my training data is 11 by 600, isn't it? So from the 11 by 600 data, next time a new gesture is being shown, the robot has to identify what is the specific intention he or she is showing to the robot. For that, there is something called a fuzzy logic based system can be developed. Does anybody have any idea what is a fuzzy logic based system?
Yes.
Some idea. Okay, you have some idea. So you know that the real world mathematical data most of the time they are linguistic in nature. For example, if I ask you what is the temperature of this room now, you can tell me that it's moderately comfortable. But you cannot tell me what is the temperature on 22.7 or 21.8. So fuzzy logic was essentially for converting the linguistic information. How can a mathematical branch can be developed using linguistic information? Most of the data in the real world is qualitative, they are not quantitative. In any case, the thing is that some rule bases are developed that if this happens this and this happens this, then output is this. So it's like, for example, they found out if the roll angle is between 60 degree and 80 degree, each angle is between minus 20 degree and 20 degree, your angle is between minus 20 degree and 20 degree. And you remember that from EMG we had 8 standard deviation signals?
Yes, sir.
You can again take the average of those 8. So if the average value of those standard deviations are between 5 and 10, then the robot will understand that the human is asking for an object. I need the object. This is how the rule base of a fuzzy system can be written. Similarly, can you see? 1, 2, 3, 4, 5, 6. How many intentions? 6 intentions. For each intention, there is one specific fuzzy rule. And within those fuzzy rules, there is one particular block which I have shown as in red one, highlighted. Why? That block, the output intention is give. It is a very complicated scenario, tricky scenario. So the robot has understood that as a human being I am trying to give an object to it. It has understood that he is trying to give me an object. Problem is, Say as a human, I may be able to carry a 2 or 3 kg object. Maybe the robot is a lightweight robot. The robot cannot carry that 2 kg object, isn't it? So even if it has understood that I am trying to give the object, the robot has to understand whether the object is a heavy one, whether the object is a large one, and whether the object is lightweight and small one. If it is a lightweight and small one, it can carry. It can take from me. But if it is a big one, if it is a heavy one, then it cannot take the risk of taking the object from me, even if I want to give it to it. So within that give category, can you see that there are 3 specific varieties? Give large object, give heavy object, give small and light object. All 3 are basically part of these 3. Can you tell me where is the difference in these 3 coming?
Standard deviation.
Standard deviation. Look at these values of the roll pitch. They are not changing. The only change is coming in these parts. Why? You can understand. If I am carrying a heavy object or a big object, where it will mostly get reflected, the way I am holding it, the EMG signals will vary. The muscles will vary in their response. In turn, EMG signals will vary. In turn, their standard deviation will vary. So you can understand the way the experimentations were carried out, that for a small and light object, standard deviation was quite small. On the other hand, for a very large object, it was very high. So essentially, how many intentions are you are going to determine? You tell me. How many intentions are there actually?
8.
8, exactly, because 6th one is basically 3. So 5 plus 3. So essentially, there are 8 fuzzy rules. And there is he knows about a little bit of fuzzy logic. In any case, the main thing is that from these 4 information, some mathematical branch is there which calculates this intention. So that mathematical branch, okay, because I have many other 3-4 other applications also. So that is why I am not going into the very detail of that. Maybe some other day, some other time. So these are the exact equations that you will have in fuzzy logic. He understands that you can associate. It means if that phi angle is between its low value and high value, theta angle between its low value and high value, psi angle is between its low value and high value, and standard deviation average is between its low value and high value, then certain intention is being activated. Let me go back to the previous slide. That high value and low value, which are those high values and low values? For roll was phi, isn't it? Phi, theta, psi. Phi low value is 60. Phi high value 80. Theta low value minus 20. High value 20, and so on. You can understand. Accordingly, those values are being calculated, and the fuzzy logic from there will determine what is the output. The beauty of fuzzy logic is that in any crisp rule-based system, either rule 1 will get activated, or rule 2 will get activated, or rule 3 will get activated. In fuzzy logic, more than one rule will get activated at the same time. And it's a judicious combination of all those which will finally determine what is the final output. For the moment, I have not included in this part. Okay. So just have a look at the experimental results. See, this is the first position. There are some objects here. The robot is standing like that. Robot is not moving, just standing like that. A human comes. From this tray, it picks up a blue object. So what does that mean? The robot, the human is trying to say that I want to give you the object, isn't it? From this information, see, the robot has not yet moved. Now look at the sequence of the robot movement. Robot has deciphered from this, because he is wearing that black band. From that, the robot has deciphered that this guy is trying to give me an object. So once it deciphers that intention, the robot moves, comes here, goes there, picks up the object. Okay. Now see, how does the robot go from here to here? Can you tell me? The robot was here. Till now, what I have discussed? What was the intention? And how was it decoded? Is it the end of that algorithm? No. I told you there was a third block. What third block? That the robot has to move from the present state to the target state. using some control algorithm. But again, we are not going into the detail of that. Even in that research paper, they have told that standard PID algorithms, PID controllers can be used for that. That means the robot knows where its end effectors X, Y, Z coordinate in the word frame. From there, though, the robot has to understand what is the X, Y, Z coordinate of this particular object. And then the robot has to move from here to here to pick the object. Once that is done, it comes back, puts it back in this particular position in the tray where it is supposed to be. It just goes back and then it stands still. Have you understood? Is it okay? This is human to robot. Another thing will be what? Robot to human. See, I think now I need not explain each and every step separately. Robot to human, you can see that the robot, the human has shown the hand. Robot, I want the object from you. Please give me the object. I need the object from you. So need is basically, as soon as it is shown, it has picked one object based on the human being and come back to its original position. Every time the robot will start from this position, will carry out the work and come back to its original position. That is the basic object. Okay? Now tell me what is happening in this slide. In this slide, see, the robot has understood that the human being is trying to give it some object. But the object is very heavy. You can have a look. This is a heavy object. What is this one? I think that is a large object. This one is a heavy object. What has happened? The robot has understood in all three positions that it is the human being is trying to give me an object. But here it has understood that it's a heavy object, another large, here the heavy. Can you see the robot has not moved? The robot has understood what is to be done, but it has not carried out the instruction. Why? Because it cannot carry or it cannot handle that large or hugely heavy object. When it has understood that it's a light object which can be handled, then only it has moved and has taken the object from him and in the right place and gone back to its own position, original position. So this is how this particular algorithm can be utilized. Okay, I'll go to the next slide. Next one. Tell me, is there any question from your side for this particular configuration? This particular problem.
Sir, whenever the object is on the table and we need the object, then how the robot can understand what is the weight of that object?
Because you will be safer. I want to give that. I can also. So for these two situations I told you, this one is a heavy object, this one is a light object. EMG sensor signal will be different. In the fuzzy rule base, it will be deciphered that the intention here is to transfer a light object. Here the intention is to transfer a heavy object.
But whenever we need the object,
then there is no problem. They have assumed that whatever the object the robot is going to give is a small one that they can take. Your point is absolutely well taken. Probably they are working on that in the second part of the algorithm. That even from that particular tray, the robot has to understand that okay, this is a very heavy object. Even if he wants it, I cannot deliver it to him. The problem. See, this is the way. The beauty of robotics is one problem. Every problem is a challenging real world problem, and from that same real world problem, the second problem generates. In everyday life, the way we move, similarly like that. So somebody can come and solve that second part of the problem. Here they assume that robot is as if when it is picking up, the object is a light.
Sir, I have one question. That they have applied fuzzy rule and it is very interesting.
Actually, not only fuzzy rule. If you go, I have shown two things. One is fuzzy rule based, another one is hidden Markov model that they have utilized.
Okay.
In that part, there can be hundreds of algorithms used. They have used two, out of which I have explained one. Now you tell me if your question is probably already answered.
Part of it, and another thing is that I was thinking that they were using neural network kind of machine learning algorithm.
The hidden mark of model philosophy is like that, basically some data driven. But this is a classical case of utilizing a neural network problem also. They have utilized fuzzy. Fuzzy is basically another, but somebody can utilize a neural network there also. Similar thing, absolutely okay. Somebody can do that. Actually, the fuzzy logic system.
But fuzzy is very
simple to understand. Very simple to understand. Actually, here the problem formulation and the hardware part of this particular work is more important. So in the algorithm development part, they have only concentrated on very specific things, very standard things. Just by using it, I can get the result out of it. They did not concentrate much on that. They left it for people like you and me, that okay, you can go and explore like that. The way they have configured this problem, it is a completely new one. I have not come across any such work before these people came and proposed it. That was the original contribution of it. Because with so much original contribution, what happens in real world, people will not put everything in one research paper. Probably they have gone on and given a second or third research paper where further modifications are being reported. Okay.
One thing, sir, can be just one point. Say if the rules will be decided, then the fuzzy will be operating very well. If the neural networks will come when there will be not, the challenge will be more numbers of things will be comes to you, then the neural
That is
network.
possible, because say here it depends on, say for example, we have trained the entire system using 10 volunteers, among which you were not present. Now you come and show a gesture that may not belong to the original training data set, then what will happen?
Yes.
Then the fuzzy system may not work at all. Isn't it? You have that phi L, low value and high value. For your case, maybe the low value is much lower or high value is much higher. Fuzzy fails to understand that. So it definitely, but all those problems associated with standard, fuzzy and neural will also be equally applicable here. But these people more concentrated on the problem formulation rather than their solution part. Solution part they use standard logics. Okay? Can I move forward? Okay, now see, we academicians, whenever we get an opportunity, we blow our own trumpet. We do not let go any opportunity when there is an opportunity for us to blow our own trumpet. So I am going to discuss couple of algorithms or couple of contributions that we have made in this particular area. Only difference is that your original lecture title, if you remember, is computer vision based gesture recognition. But although I have given the title, I have also considered non-computer vision too. The first one is not computer vision. Our works are essentially for computer vision based gesture recognition in robotics, collaborative robotics. So let us see how it can be carried out. Two broad varieties of research work that we have worked on till now in this particular problem domain, and we are still working on that. One is we show the human gesture, natural human gesture to a robot, and how much more sophisticated algorithmic part or artificial intelligence part can be implemented for robot navigation. Another problem that I shall discuss is that one will be human gesture, basically using hand gesture, very simple natural hand gesture. But the problem, I can show what is the complexity of that problem. Second one is that we will not show hand gesture. What can be other different varieties of gestures can be shown. So we have shown some, we have utilized some flat stick based visual cue. So those two kinds of problems that I shall discuss, how they can be solved. These are some of our salient contributions of the entire group in last 5-6 years in the area of vision-based collaborative robotics. Vision-based collaborative robotics. These are some contributions. Essentially, part of Pritam, Shoibal, and Devoshi's work. Pritam has completed his PhD. Shoibal is almost towards his completion. Devarshi was a master student with me, who is now started doing his PhD in ISC Bangalore. So we'll show some of their contributory works. Okay, so these are the works that we have carried out in this particular domain. First one, which is a human gesture based collaborative robotics for robot navigation. How it can be used. Can everybody see this? Because I need to use the board extensively now. So it's okay, everybody can see. So the basic problem in its simplest form is quite simple. We show 4 gestures to a robot. This one, this one, this one, and this one. And from the 4 gestures, you try and understand that robot has to speed up, robot has to slow down, the robot has to go towards left, robot has to go towards right. We have using 4 gestures, it can be further increased. That is, the scope is sky high. Okay, looks a little bulky. So this is the real robot that we utilized. This is the indigenously developed robot, courtesy Professor Anjan Rokke, who was also my professor and other figure of our group, the mentor of our group, and will remain the mentor of the group till the day I die. This differentially driven wheel mobile robot developed, it contains, you can see, this is the camera actually, vision sensor. That is a Sony made vision sensor, IRS 219. Very well known and very, what should I say, medium price, not very high price.
So range of price?
It was of the order of few thousands, not more than that, not too much. Just maybe the price has changed now.
Yes.
So you just type it and you will get the price, and it's abundantly available, no problem. And these are the ultrasonic sensors along with that. We have also carried out work using the ultrasonic sensors, but because today's discussion is only on vision, so I am going to discuss only about vision related problems. You can go to internet, look at our profiles and can see what are the other works we have carried out using ultrasonic sensors. Not part of today's lecture. So, what the entire overall scheme, explain each and every point separately. First point, for each such machine learning based system, there has to be a training database in neural network sense. We will call it by a different name. We'll come to it later. For you, for the moment, it's also written gesture database. So prepare a hand gesture database, training database. It means you and me or everybody will come and show to the robot some hand gesture, the images are being taken. Appears very simple for the moment. Some pre-processing is being carried out, some segmentation is being carried out over that to make the images further legible. How many, I hope some of you at least are conversant with the basics of image processing. Some of you at least, I hope. Okay. Some of you. Because in a varied audience, I cannot expect everyone to know everything. It's not possible.
Those kind of things are like masking, thresholding, those kind of things.
Basic things, basically. But if you understand the logic, somebody can go and start doing the work in some other field also. The other parts are right at the moment very mathematical. Let me go inside slowly. Whatever is being written, I'll explain each and everything. See, look at the images. This is for one particular gesture, another one, 4 particular gestures. Can you tell me what is the difference between these, the first row of images and the second row of images? Can you identify there is a basic difference?
One is right hand
Gap between the fingers.
Not so minute thing. The gap between fingers, because in normal situation I cannot direct you that keep the fat gap like that. So we have kept those That flexibility is there. When you are showing gesture like that, you will come and show like that, I will come and show like that. Both are acceptable for me.
Contrast.
Maybe next time you will come and show like that. That is also acceptable.
The difference in
Right hand
contrast.
and left hand. Right and left hand.
Contrast. So, sir, contrast.
What he is telling us, contrast is basically, it means, if you look, this image is a relatively good, well illuminated background.
Yes.
And look at it, this is a much more challenging situation
Yes.
where the images are dark. Actually, say in Indian industrial scenario, what will happen? See, this room actually simulates one industrial scenario. In some places there will be very good illumination, in some places there will be not so good illumination. The algorithm should be able to work in most situations. Most of the, what should I say, ANN or deep learning, those kind of algorithms, all database machine learning algorithms, most of them, they actually work on regular variety of data. They do not consider too many challenges in the data set, too many variations. But in real world situations, when you try to employ those algorithms, there will be many varieties of the problems. So the solution must be a very robust one. So if under very good lighting condition, if your performance, say for example, is 99%, and you go explaining that it's very good, but finally when you use it for a very low lighting condition, if that becomes 30%, that algorithm is no good. It may be good in Western countries where the ambient conditions remain invariant, but not in our countries, not in developing countries. So that was our main challenge or motto of our research, to develop such algorithms in more and more challenging situations rather than normal regular situations. In normal regular situation, almost every algorithm does very good. Somebody is doing 99.2 and somebody is doing 99.0, it actually does not make any difference. The point is whether it's still able to hold to its performance when the situation is degrading. So our objective is that, okay, these are the hand gestures. I can develop an algorithm which will perform very well and identify these hand gestures. But whether even under this dark condition, the algorithm is still able to hold on to its performance or not. That was the very important. That was the main focus of our research, to develop such intelligent algorithms for robots in more challenging situations. I hope I have been able to see the image, show the images here. Another situation, have a look. This is in robotics term, in navigation term, this is called, if I move, say for example, you can directly have a look at me completely. If I move here, what will happen? A portion of me will get occluded.
Obstacles are there.
Some obstacles are there because of which my entire contour is not available to you. You cannot see me completely. So this happens that when an object moves in a real world, there are some occlusion. Something is occluding the original object. So even under that condition, what happens? A portion of the hand is getting occluded. Whether my algorithm or your algorithm is still able to identify the same gesture being shown. And the amount of occlusion in one image can be 10%, in another image can be 70%. Whether the algorithm is still able to identify that, okay, the same right hand in this right direction was shown or not. That was the point. So as I mentioned, these are some photometrically challenged situations with illumination conditions. We call it normal condition, dark level 1 and dark level 2. That was our work in this particular. Later we moved on and we made the challenging conditions even harder by making it dark level 3 and dark level 4. Your point will be, sir, how did we simulate it? What did we do? In our laboratory there are 4 tube lights. So, and through the windows, exactly similar to this situation, the sunlight is coming. So when the sunlight is coming, all 4 tube lights are on, that is a normal lighting condition. Very good. Then gradually we switched off 1 tube light. That is lighting condition dark level 1. Second, 2 tube lights, 3 tube lights, 4 tube lights, all switched off. Dark level 1, 2, 3, 4. Are you getting my point? So this is how the dark levels were simulated in our experiments. Can you see the images are getting even darker? And there are more bigger, what should I say, the obstacles are coming, occlusions are coming. So as I mentioned, if I can identify which gesture it is, up or down or left or right, From there, I can write my own lookup table. I can say what is up meaning, what is down meaning. So for us, up mean move forward with increase speed, move left, move right. But you can develop your own hand gesture and you can associate your own lookup table with that. It's your job. You can do that. Everybody is free to do that. Now the question comes. Okay. Before I go into this mathematics, let me. Okay. Now I go to the book. Have a look at the screen. At the same time, concentrate more on what I am doing on the book. Suppose each image is captured by that Sony sensor of that robot is of size 30 by 20, which we have shown here in a small 4 by 4, but actually let it be 30 by 20. So if it is instead of 4 by 4, it is 30 by 20, that two-dimensional matrix of the image can be, what does happen here? Image means there are some intensity values here, isn't it?
Yes.
If there is 8 bit of data, then 8 all zeros to 8 all ones. 8 all zeros means intensity value is 0, 8 all ones means intensity value is 255. All zeros means black color and all ones means white color. So in the dark, the gray levels syntax, we can say that there are 256 gray levels available to us. And if I have a 30 by 20 image, the 30 by 20 image can be converted to a vector of 600 by 1 size. 30 by 20, how many total number of pixels? 600. They can be written as a form of array. How it is written, you can see that. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 5, 6, 7, 8, and so on. Understood?
Yes.
This is the classical way of representing an image in a vector form in the raster scan. You go like that. Okay, and put it in the vector form. Understood? So then, a 30 by 20 image is converted to a 600 by 1 vector. Now, say suppose 4 gestures were there. If you remember, 4 hand gestures. Each hand gesture, I have 250 images or 300, say for example. How many total images are there? If for each gesture there are 300 images undertaken, upward, either from you or me or from all of us, how many gestures are there? 1200. For each gesture, it means an image has been upward. For each gesture, an image is converted to a 600 by 1 vector. So what is the total dimension of the matrix now? 600 by 1200. For one image, 600 by 1. One image 600 by 1. 1200 such images, it becomes 600 by 1200. Got it? So, this image or this matrix is like this matrix, isn't it? So this matrix, the way we solve it, we are utilizing something called sparse representation and dictionary learning. I'm coming to it. So kindly repeat this part, please. Each image is of size 30 by 20. 30 by 20, each image has been converted to a vector. The vector size is 600 by 1. Now you, me, we all are volunteers. From us, the robot captures 1200 total images of 300 images for each gesture. So how many total images are captured? 300 into 4, 1200. For each image, what is the vector size? 600 by 1. So what is the matrix size? 600 by 1, 1200 times. 600 by 1200. Now look at this image. Out of this 600 by 1200, this is gesture 1, isn't it? One block is gesture 1, gesture 2, gesture 3, gesture 4. I could not make it equal sized. Anyways, I hope you have understood that. 600 by 1200 is the total size. Tell me what is the size of gesture 1 database? 600 into 300, correct? Because there are 300 images per gesture. Is it okay up to this point?
Yes.
We call this entire data in the database, which in ANN or dictionary or in deep learning is known as the training database. In our system, this is called a dictionary, because a dictionary houses all the words. Okay, it comprises every possible combination. So that is why this is called a total dictionary D. The data, we were asked to come to this college on Sunday. Yes, sir, please come and give some images because we want to develop our system. We came on Sunday and we gave all those images. Say for example, let us consider that there are 4 gestures from all of us have been acquired actually on Sunday. On Monday, we again come. But this time, the robot is actually implemented in real life. When it is implemented in real life, now I show an unknown gesture, robot has to understand which gesture it is. Isn't it the problem? So I come and show my left hand, say for example like this. The robot has to understand which type of gesture it is, how it can be done. That means the image I have taken is 30 by 20, is it okay? What is the 30 by 20 image converted to a vector? 600 by 1. So this is the unknown image Y in vector form. We have to understand to which gesture class it belongs. Is it okay up to this point?
Yes, sir.
So I am trying to find out, I am trying to determine a mathematical model, a linear mathematical model, such that this relation holds good. Like A is equal to B into X. We call it Y is equal to B into X. What is Y? The unknown image, unknown gesture. What is D? The dictionary we created. What is the dimension of Y? Y 600 by 1. What is the dimension of dictionary? 600 by 1200. Then tell me what is the dimension of this X? If this is 600 by 1, this is 600 by 1200. What is the dimension of X?
1200 by 1.
1200 by 1. I have to solve for this unknown X. Have you got it? By some method. By some method for the moment, solution is obtained. Solution is obtained. And let us assume that the solution is correct. If the solution is a correct one, now look at this matrix. Y is equal to Bx. Let this G1, let this dictionary, sub-dictionary be D1, D2, D3 and D4. Is it correct? Okay. Sub-dictionaries. If these are sub-dictionaries, then this vector X unknown can also have some sub-vectors. How many such sub-vectors will be there? 4. If there are 4 dictionaries, 4, how many or how can they be written? This is X1, X2, X3, X4. Is it okay? 4 sub-dictionary or 4 sub-vectors. Then tell me Y is equal to Bx. What can I write here? Y is equal to Bx is same as D1 X1, D2 X2, D3 X3, D4 X4. Have you got it? Is it okay? Now tell me what is the dimension of D1?
600 by 1.
600 by
One.
1 কি করে হয়? D1 is a dictionary. D1 is this dictionary.
Okay,
600, 400.
600 by 300.
300.
400. This is 600 by 300. Then what is x1? Size
300 by
300 by 1. There are 300 coefficients here. 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 Now, if you have been able to correctly solve the problem, what will be the nature of the solution? The nature of the solution will be, say, for example, this unknown image. Let it belong to the gesture 2 database. Can you tell me what will be the nature of the solution X? Ideally,
Ideally, D1, D3, D4, these coefficients will be very much low and D2 coefficient will be very much high.
so ideally what should be value? Ideally what here exactly correct what is saying, this X2 unknown image is belonging to gesture 2. X2, this small vector, will contain high coefficient values. And ideally these coefficients will be all 0,
And that
this
will-
all 0 and this all 0. So then the solution vector of 1200 size, there are 1200 coefficients in X, out of which 900 should be zeros. When you get a vector containing so many number of 0, it is called a sparse vector. So obtaining such a solution is known as a sparse representation or sparse coding solution. Do I make myself understood?
Yes, sir. Very
Now,
clear.
is it okay? Now, in practical situation, what will happen? In a practical situation, what will happen? These values will not be exactly equal to 0. These values will not be exactly equal to 0, but small values. So, what will happen? The x2, these coefficients will be significant. x1, x3, x4, all these coefficients will be almost 0. How do you use that data? You calculate something like this. Can you tell me what are you doing here?
This is not too good.
You are what is this type of norm? Exactly correct. What is this norm? This is the L2 norm. What is L2 norm? L2 norm is the Euclidean norm we all know. Say for example, if I have a vector A, B, C, its Euclidean norm is root over a square plus b square plus c square. Now just extend that instead of ABC, I have x1 to x100. Euclidean norm is root over x1 square plus x2 square up to x100 square. Okay? So that is how, what are you trying to do? See, y minus b1 x1, what will be the result here? You tell me. Ideally, what will be the result?
0.
How can it be 0? Because x1 all coefficients are 0. So d1 x1 will be 0.
Yes,
Isn't it? So this,
it will be y.
it will be y. And same will appear for d3 and d4. You are talking about 0. Where will it be 0?
For the
For that second gesture class. Because that was the unknown image class. So that there it will be, y will be then d2x2, isn't it?
Yes, sir.
So you calculate y minus d2x2, ideally this should be 0. But practically what will happen? Practically what will happen is that y exactly will not be d2x2 but very close to it. That means this L2 norm will be a very small value.
Epsilon kind of.
Epsilon kind of value. And for all other classes, that will be very high. So for each and every class means that each and every gesture. Can you tell me what I am solving now is basically a classification problem.
Yes.
Finally, I am solving a classification problem. How many classes? 4. Because I have 4 gestures. You can develop a 10 gesture situation, it will be a 10 class classification problem. The only thing is that in that case, the unknown image will be assigned to that class for which y minus dixi will be lowest. Then do not. This is known as the representation residual. If you represent the data correctly for a particular class, what will be the representation residual? You tell me 0. But practically residual is what? That you are left with something. Ideally correct representation, no residual. Practically what will happen? Very small. For all other classes, representation residual is high. What does that mean? That image does not belong to that class. So solve this particular problem for this X vector. Obtain the X vector and for each and every class calculate the representation residual to whichever class the representation residual belongs. Assign the unknown image or unknown gesture to that class. Tell me if it's understood or not. That is the basic spirit of sparse representation.
Very interesting. You are explaining so lucidly, very interesting.
So if there is any question, you can ask me. Is it okay up to this point? There are many other mathematical intricacies which I am not going into detail right now because the audience is a little varied. So too much mathematical depth because the mathematics is intricate, let me tell you. I am trying to explain without going into the very detail of that, but still explaining the spirit of that. If I have an audience which is exclusively for, say for example, only for computer science, electronics, electrical and mechanical, then I will go into the very detail. Otherwise, because of a varied audience, mathematics may become too boring. Trying to keep the presentation as much as possible, not going into the very detail. So okay, let me not go into the detail. Now there is a problem. Okay, we have understood the problem, how the sparse representation or sparse coding problem is carried out. Now, okay. Let me rub it off. I have come across now. I think the more important point will be, although I have, I think about 4 configurations. We are in the second configuration, but running through all of them is not important. Let me move slowly so that whatever is understood. If you ask me, I can run through and go through the entire presentation, or I can with the present speed, I can try to explain as much as possible. Which one will you prefer?
Sir, that is whatever you are doing, sir. That is.
Is it okay? Because otherwise, what will happen? I will run through it, but will not remember anything. Okay, nothing will stay with you. The presentation is a very long one. So, because now whatever we are entering, I will try to explain slowly because these are very intricate mathematical matters. But if you understand it correctly, slowly, it will not be that difficult. Let me tell you. First thing that I have done, till now, I was using this linear mapping. It's a bit cold, huh? Y is equal to d into x was there. I have changed, not I have changed, basically because now I am talking about a presentation from another boss. In that paper, they have used y is equal to d into alpha. So no change. Only thing is that whatever I discussed as x, from now on consider the vector x as vector alpha. Because in that paper, in this paper, they have used x as alpha. Mathematics is same. Y is equal to d alpha. This was my basic sparse representation problem. Now see, I have come across a new term, regularized robust coding. The thing I discussed was what? It was called sparse coding. sparse coding, basic deep learning, neural network will what find? If all my training database data, in our case gesture images, are taken under good lighting condition, then there are no challenges involved, so-called challenges involved, only mathematical challenge is there, otherwise there is no environmental challenge present. All of them will do what? Wonders. Now consider a situation where our problem comes. What is the problem? I have used a data set not only comprising the basic illuminated images, but there are some images which are illuminationally challenged, photometrically challenged. There are some images which are having occlusions. Will my alpha or X solution still be activated? Of course, you can understand that the performance will degrade. If the performance degrades, then what will happen? Y minus dx or y minus d alpha ideally was what? Ideally it was basically for each and every class. For one class it was almost giving 0 values, for other classes very high. Now what will happen? Even for the correct class, the error values will be significantly higher than the previous class. So now you simply consider this y minus dx. Is it a vector or a matrix? You tell me. Vector. Why is a vector? I can only subtract a vector from another vector. This is 600 by what? This is 600 by 1200, isn't it? And that one was 1200 by 1. So if you subtract y minus dx, actually from here, let me call it alpha, okay? Y minus d alpha is basically a error vector. And the error vector, what is the dimension? In a normal situation, that L2 norm of the error vector will be a reasonably small value. But when that photometric challenge comes, when the occlusion comes, that error vector, if I take the L2 norm, what will happen? It will be significantly higher value. Error will be quite higher. What does that mean? In that E vector, there are elements which will be having higher values than the previous one. This E vector, just have a look. This E vector is now, am I correct? There are 600 entries in it. How did you come across this? You come across this like that. There was y, and then minus, there was this d, multiplied by there was this x. Am I correct? This was the basic thing. Alpha. This, if you look at this expression, the expression is not important. Okay, the expression, this is the basic sparse representation equation actually. That sparse coding I told. What does that mean? It is L1 norm. L1 norm means what is the, L1 norm is for each and every element in this vector, you take the mode of that and then take sum of it. I told you that the sparse vector means there will be most number of zeros and very small number of non-zero values. So say for example, ideally, how many zeros will be there in this vector alpha? Ideally, no, zeros, how many zeros will be there? Zeros will be 900 and 300 will be non-zero values. Then if you calculate L0 norm, L0 norm means how many non-zero elements are present in a vector. So what is the ideal L0 norm of the vector alpha? 300. Now solving for, that means this vector, for this minimization of this reconstruction such that the L0 norm should be less than equal to 300. solving that problem mathematically is a very difficult thing. They are from computational science, computer science background. They know this is called an NP hard problem, non-deterministically polynomially hard problem. Solving it is very difficult. So people have shown that if a problem has to minimize the L0 norm, that means sparsity has to be enhanced. If you can minimize the L1 norm, equivalent result is obtained. But solving for minimization of L1 norm is much easier compared to solving for L0 norm. What is L1 norm? L1 norm is nothing but in a vector you take the mode of each value, each element, and take the summation of it. Here, sigma mod of I is equal to 1 to 600. This is the L1 norm. So people say that if this value becomes minimum, that means automatically there is very small number of non-zero values present in the vector A. That is the idea. Okay. So anyways, this is the basic way of solving the sparse representation problem. Now the challenge is more because the images are challenged. For that, okay, let me proceed forward. More, let me show you the graphs and let me try and explain to you. Okay. Vector. Error vector. The error vector, if you calculate the corresponding error values, so if you calculate that error values, look at this vector previously. E is not given here. Okay. E is basically nothing but that y minus d alpha. Okay. So each and every value of E1 to E600, compared to the normal situation, the values will be what? Ideally, either remaining to the previous value or more than that, isn't it? Are you getting my point?
Yes, sir.
E1 to E600 or all those error values. In challenging situation, what will happen? Either they will increase from the previous value or remain same. They will not get down most of the time. Now, say for example, if you consider the situation of this particular image, I have the original image vectorized as y. I have the original image, its sparse representation is d into alpha. Y and d into alpha are the same. Are you getting my point? What I am saying? You have an original image. The original image was vectorized 30 by 20.
Yeah.
It became what? It became some y. Its model. What is its model? D alpha. D alpha is what? 600 by 1. Can be converted to the image 30 by 20, rolled back. Will the same image come or will there be some difference? Some difference, because each and every pixel there is some error, na? This E1 to E600, what are this? E1 is the error of the model in pixel number 1 and E600 is the error of the model in pixel number 600. Normal situation, the model error small. Challenging situation, either remaining the previous values or getting higher. Are you getting my point? E200 is basically merely the pixel of 20,11. Previously in the model part the value of the error was 0.1. In challenging situation it is 0.15. So in normal situation what will be the error in the model? Very small. So most of the time can you see that error most of the time, say output, what is the error values, what is the range, minus 0.02 to 0.02. Okay, let me show it. How many of you are conversant with the term probability density function?
Yes.
Some of you must be knowing. যারা একটু অঙ্কের বা ফিজিক্সের দিকে থাকেন তারাও বলতে পারবেন। ওকে।
So actually we are doing optimization technique.
তাহলে তো ভীষণ ভালো, মানে Basically the
Basically, we are doing optimization
Exactly.
technique and finding out the error.
That is exactly the
The
point.
LMS algorithm,
So even if
RMS
you don't know image processing, signal processing does not matter at all. It is basically optimization and linear algebra.
Linear.
That is enough to understand this entire thing. That is what I am saying, that there is no need to understand whether you know the image processing, signal processing. Those things are not required at all at the bottom. See what I am trying to say. Total number of pixels are 600. Most of them, error will be very close to 0, not exactly equal to 0, but very close to 0. Let the maximum value of the error be 0.02 and minimum value of the error be minus 0.02. Isn't it little like that? Let us assume that this total range is divided into 10 equal parts. তাহলে আমাকে বলুন, then you tell me what is the total range? 0.04. So 0.04, 1/10 of that is 0.004. So that means here one particular block will be from minus 0.02 to minus 0.02 minus 0.004. Is it okay? Minus 0.016. Then the next block will be minus 0.012. What is this last value? 0.016. Is it okay? Understood? I have divided the entire range into 10 blocks. And how many pixels are there in the image? 600. So for each pixel there is an error. If the error value becomes false between 0.016 and 0.02, in the histogram what will happen? The count will increase by 1. So maybe total number of pixels having error between 0.016 and 0.02 is 59. Then this is between 0.012 to 0.016. 75. Are you getting my point? So there will be how many such buildings? 10 buildings, because there are 10 ranges that I prepared. So maybe you will find that the buildings are like this. What is the solution? Be like that. What will be the total count of these values? 600. So now you divide every value divided by 600. What is the total count now? 1. So now what is the total? Now if a new pixel comes, after modeling there will be some error associated with it, but whatever be the error, what is the total probability of having any value? Is 1. So that means if you convert it to a graph, then this gives what is called a probability density function px, where integration px dx is what? 1. What does that mean? That every new pixel comes, its total possible probability is what? Total area under the curve. What is that? 1. But you can see that around 0, that means minus 0.0022 plus 0.002, here the maximum number of pixels will lie. What does that mean? For a new value, unknown value, highest probability will be there that it will be in that zone. So maybe maybe this count was 175. When it was converted, its probability became what? 175 divided by 600. So any new pixel having an error between minus 0.004 to plus 0.004, that value will be in the range of probability will be 175 by 600. So from there you can say this is the empirical, actually from the image, this is the empirical curve that I have got. What is that empirical curve? Around 0 the probability is higher. Why? Because most of the pixels error will be quite small, around 0. But for some pixels the error will be quite large, but the number of count will be quite small. So that will be represented by what? Can you see that the blue part here, some value is there, but the value is very low. Not only here, but also on that side. Tell me whether have you understood or not. Again, till now, this blue curve, tell me, is it for a normal image or for a challenged image?
Normally.
It is for a normal image. For normal image, the modeling is so good that around 0 most of the error will be present. What does that mean? That a new pixel comes, error in modeling will be very close to 0. Now challenges come. When challenges come, what will happen? This graph, now right now you just draw the curve like this, isn't it? But when the challenges come, maybe the curve will be like that. Are you getting? Where it will get more affected? Towards the tail.
Yeah.
Because there will be no more population of pixels having more error. So what does that mean? There will be more error in this part. So count will be more here or count will be more here. Then the standard way of using a Gaussian distribution or for example a Laplacian distribution will not work. For each and every image you have to prepare a new probability density function. And that probability density function, how do you make it? We can see that they are showing. Can you see that this is the blue curve? Ideally, I should be able to map that from this particular situation. Look at this particular situation. This is for this particular image. Original image, very good. Corrupted image. Challenged image. Original what was proposed in a face recognition paper, we brought it to the robotics domain. Okay, but from here you can understand the problem. So here, can you see that the curve is getting more undulated like that? Mapping that probability density function becomes a very difficult job. So regularized robust coding actually solved that problem, but probably if I go further into the mathematics, I hope you have understood the basic spirit.
Yes.
Okay, otherwise now what will happen? I have to explain. Okay, let me do one thing. This much I can do. Of course, this is not that difficult. See. Okay. See, in a normal situation, as he was mentioning, if it's a normal image, even in normal image there are errors. In a normal image, I can use that Gaussian distribution. What will that Gaussian distribution tell me? That around 0 there will be most of the errors, and around 0, either on the left hand side or on the right hand side, more towards away from 0, there will be less errors. Understood that? Now, because of the challenging situation, what will happen? The curve, instead of this, the curve will be like that, isn't it?
Flattened.
And that with image to image, it will vary. So, obtaining the probability density function from that situation will be difficult. So, what did they do is that you can represent it like this. See, this is the error. E. E was obtained y, leave aside y. Look at d into alpha. This d into alpha, look at this d into alpha. When you calculate d into alpha, this is nothing but first vector multiplied by the first coefficient. Second vector multiplied by the second coefficient, isn't it? At the same time, it can be also shown like, say for example, E. I have E1, I have E2. E1, how can I calculate E1? Can tell me? E1 is nothing but this row multiplied by this entire vector, isn't it? E1 is nothing but R1 into alpha. What is E10? What is E10?
R10 into alpha.
E10 is R10 into alpha. E10 is nothing but R10 into alpha. So each and every row from the matrix D, now we are considering. at the same time, every time alpha vector is considered completely. So in that situation, after calculating this E1, E2, E3 and so forth, say this error in position 1 and error in position 2, is there any correlation between the two? Depends on the model. Whatever be the alpha vector has come, from the D matrix separate R1, R2, R3 rows will come. R1 into alpha, R2 into alpha, R3 into alpha. E1 and E2 have no correlation. E2 and E3 have no correlation. So they can be considered, those who are conversant in statistics, I-B distribution. Does anybody know? Identically, independently distributed. It means for each error, I can draw a probability density function. But each error probability density function is independent of each other. Separately you can draw. And if you draw a Gaussian, the mean and standard deviation can change. But for you can consider as if the same mean and standard deviation for each one of them. So to consider that, you have to consider identical. Identical means all are same PDF, normal. And independent means what? How E1 is varying is not dependent on E2. How E2 is varying is not dependent on E3 and so on. Tell me. Okay. But again, I don't want to go into further in this algorithm because this is maybe a little tough for some. Maximum, like, go straight to the next problem then. Let me discuss a little bit of that. Whatever you prefer, you tell me. Because the mathematics will get a little complicated now. Go to the next one. Anybody who wants to discuss this separately, I am always available. But for others, it may be too difficult to at this moment. See the amount of mathematics that I have to explain. Okay. But if you want to implement these algorithms, you need to understand that. What I can tell you is that, okay, finally, just two lines to sum up what was the research contribution. It was shown, what was the problem? The main problem is that I have to identify an unknown probability density function. Do you remember that? And that will be for each image, it will be different. And finding that probability density function was finally solved using two basic concepts of optimization they may be knowing: maximum likelihood estimation and maximum a posteriori solution. Bayes estimation will come into play. When you implement the Bayes estimation, okay, let me just show it to you. This is the way now alpha will be solved. Just 2 minutes. I am not going to the details of the algorithm because then again I will need at least if I want to explain it clearly, more than 1 hour time is required. Otherwise, we will not understand it. See, every f theta e, I told you that for each pixel error E1, E2, E3, there has to be a Gaussian. For example, Gaussian, it can be any PDF arbitrarily. That f theta e has to be found out. And for each pixel, f theta E1, f theta E2, how many such f theta? 600. There were originally 600 pixels. So f theta E1 to f theta 600. If they are identical, then their joint probability will be what? P1 into P2 into P3 up to P600. So f theta E1 into f theta E2 into f theta E3 into f theta 600. This probability should be what? Should come to around that 0 point. So that probability should be highest then if I calculate that multiplication. That multiplication, if I take it to log of that, what will happen? Log of A into B is what? Addition. So that is why, can you see now this is the addition function. Why? I have taken log. And ideally I told you that if I only take this function and all multiply, ideally what should happen? This should be maximum. If I take log converts it to summation. If I take minus, then the maximization problem becomes minimization. This is the, I told you that there was a representation residual.
Yes.
Representation residual should be high or low?
Low.
Low. So this quantity actually signifies that the representation residual should be low. Representation residual low means what? Mapping is very good. Mapping is very good in this context of statistical signal processing means it has a high fidelity.
Identity zero error.
Zero, ideally zero error, but practically not zero error. High fidelity. High fidelity. So there is a fidelity term. If this fidelity term becomes, that term becomes slowing medium, the fidelity becomes improved. Okay, I did not go into the detail of heading. Okay, I hope you understand. But not only solving this is important, sparsity also has to be maintained. Sparsity comes where? In that alpha. From that Bayesian estimation, for alpha also, a PDF of how many alphas are there? You tell me. How many coefficients of alpha were there? Not 900. 1200 by 1. 1200 by 1. So ideally it should be 1200 at that f of alpha 1, f of alpha 2, f of alpha 3. How many? 1200. So 1200 f of alpha again multiplied. Multiplication converted to log will be what? Sigma. You can see the corresponding sigma. So that also has to be minimized. Why it has to be minimized? Because if alpha values are minimized, if you take N1 norm, what is that? Summation of all of them, isn't it? Mod of that.
Yes.
So basically, if that sigma term gets lower, essentially you are going towards a sparse solution. Both of them. This is called the regularization term. Regularization means what? Alpha 1 sparsity is maintained. And what about this term? You are trying to maintain the fidelity. Try to solve for a sparse solution, maintain the fidelity term. Even when there is the regularized robust coding means when the image is challenging. Why challenging? Because that f theta e is essentially a PDF. PDF has to be correctly drawn, tails are properly mapped. Previously in the Gaussian, the tail was not properly mapped. The main mid portion was more important. But here, tail portions are more important for robustness. So again, some steps of mathematical calculation, and from there it was shown that one weight matrix W has to be calculated. How the W matrix is calculated is the main part of this research. I shall not go into the detail of that. See, one can easily understand what they are saying. Say if residual value is high, should I put more trust in my solution or less trust?
Less.
If the residual value is high, I should put less trust. So I should give less weightage and more weightage. Less weightage. Can you see that every weight function is trying to develop for residual value low, W value high. Now high to low, you can go like that, you can go like that, you can go like that. Finding out which function performs the best is the main. RRC people, they came up with this solution. Sigmoidal curve, I think those working with neural network, they know that. Sigmoidal curve is basically the inverse of that. They proposed. So then we arrived in the horizon and we told that see what we are doing. They provided that sigmoidal curve, but in the sigmoidal curve, look what happens. If this residual value is very high, they are making the weight very low. That means they are not giving any weightage at all. We told that if our images become too challenged, too much occlusion, too much noise corruption, too photometrically challenged, then many of our pixels will be in this state. Modeling error will be like that. If you make the entire weight value 0 there, those pixels are not contributing anything to your model. So we came and we told that you can just have a look at, remember the blue curve. Already the blue curve is already there also. Can you see? We proposed an algorithm weight thresholded 3 algorithms actually. But can you see the main contribution of our what? Red and blue, red and black was our contribution. Blue was the original RRC. What did we say? Essentially, we tried to say if the residual error is low or very high, do not put weight exactly almost equal to 0. Give them some help. Give those pixels which are having very high error some respect. Don't completely disrespect them. That was a physical idea we struck first. Then in research you have to convert it to some mathematical equation. So our basic idea was that do not discard all those pixels which are having a very high error. They also have some contribution to make. So accordingly, look at this one variation, the red variation, black variation, one variety. What did we do here? Can anybody tell me? Here our idea was that if from here the blue is coming down. So what did blue say? Sorry for this slide. Original analysis said that okay, somewhere between 1 and this value, we should start disrespecting gradually, isn't it? We told them that in a very degraded situation, give them more respect is another way that at least still continue up to this point with the high weight level. So one way is to take care of this part. Another way is that don't get tapered very early. Get tapered, but get tapered towards lower. Gradually, every card we proposed came from the idea that be tolerant. Give them some respect more than what RRC did. So with that, this was second one, this was third one, and then finally what was the results? If you look at the results, this is when the images were non-occluded.
That's good.
That's okay. Okay, that's okay. See here, when compared to the basic CRC, RRC performance was not good. Anyways, you look at from RRC and its variants. Can you see that 96.74 hours was 97.83 and 98.64? Okay, this was when there was no occlusion, only photometrically challenged. When both photometrically challenged, this was photometrically challenged plus occluded. So this was performance degraded for all. Our degradation was less compared to them. And I can show you, this was for that, what should I say, dark level 1, dark level 2. Do you remember? 2 levels of darkness. In the 2 levels of darkness, look at that. When the situation got very significantly degraded, 82.97, 85.14, 80.07, 81.16. Still better compared to them. I don't say that we achieved huge improvement, but improvement which is of note, but which also says there is further scope of improvement. In fact, there are 2 undergraduate batches who are currently working to further improve upon this result, and already they have got some result which is for this situation better than that. But I can only discuss that when that paper gets accepted, it comes in public domain. Right now I cannot discuss that. But it shows that the improvements are there in the right path, but still there is still much work that can be carried out. So we are approaching towards the end. So let me take 10 minutes more. 10 minutes, okay?
Yes, sir.
So 10 minutes. I hope, this algorithm I tried to explain as much possible in detail. I hope you have understood what. So I'll show the third
graph. Actually, you have shown that
Which one?
graph, the blue graph. Previously, this graph actually the residual error.
This one.
The residual blue graph actually residual error. এটা থেকে আমরা কার্ভ ফিটিংস লাগাতে পারি না
It's possible. But curve fitting means
That
you
data
need
is available or that data has to be generated or that has synthetic data?
RRC code is available.
Okay.
Original RRC code in MATLAB was originally available for face recognition. So Shoibal, who did this work, this was his master's work, and next work will be on PhD. He converted that to Python
Acha.
and used it with our robot. So that is not available, but original face recognition RRC code is available. But that is basically a classification code. You can use it for any other one. Any other one. RRC code is available.
So that error.
That is the MATLAB code available.
That error, residual error graph actually comes from with that synthetic data or the simulation data. The error.
From the images. You want to say that blue curve.
Blue graph.
The blue curve, they have used an equation. We have also used an equation. It is not any data fitted graph. Because it is what? It is the logic is that W should be higher for lesser residual error and W should be lower for higher residual error. This is not data driven.
How we are taking the W
That is how we are varying the W. That was the research. Now you can also think that whether you can make it. You can we can do that. We can do that. So you can propose some. You can propose some method that for each and every individual image, the W should be based on data. It is possible. You can try that. We have not tried that. You can try that. Why not? You can try that. But originally it was an equation of sigmoidal curve. Whatever we have proposed are also analytical curves. Not this part is not database. Data is coming in the original RRC dictionary part. There the data is there. W is not data driven. Okay. Okay, can I proceed? So let me just have a discussion on. I told you that we have working on two varieties of gesture-based collaborative robotics. One was that simple hand gesture, but it did not remain simple hand gesture because of the environmental condition. Second one is same robot being utilized. Problem is different. Previously, we showed the gestures like that using hand. Here, we are showing the gesture, using the gesture as a flag stick cube. You can see that we actually have like this. I can show it to you. This is a flag along with the stick, pasted on the stick, and each such gesture shown to the robot means a certain navigation mechanism the robot has to follow. But most importantly, the previous research, I told you the previous algorithm, how many dark levels were considered? So, how many conditions were there? 3. Normal, dark level 1, dark level 2, as I mentioned. This was the later part. Actually, the first work was Shoibal's PhD, master's thesis work. Okay. Second work is basically in the PhD part. Then the problem was made even complicated, more complicated. You can see, this is the normal landing condition. Look at the change in the illumination level. It's so dark. Can you see that? And this was one particular flag stick. Just consider how many. You tell me how many class problem is now this one? Top left, middle left, bottom left. No flag. Top right, middle right, bottom right. How many class problem now?
7.
It's a 7 class problem. Only thing is that I have to write a lookup table for if the robot understands that there is a top left flag being shown, what it has to do. This is what it has to do. Can you understand what is that? If it sees that there is no flag, that means the robot will move straight. Top left, middle left, bottom left. That means I take a right turn by 30 degree, 60 degree, 90 degree. And top right, middle right, bottom right. I take a right turn, 30 degree, 60 degree, 90 degree. You can further increase the number of gestures, further increase the number of classes. But our problem, as I mentioned, again, more robust, more challenging situation, because the darkness conditions, or darkness lighting conditions, are being made further darker and darker and darker and darker. Actually, we wanted to do dark level 5, 6 also, but we only have in that laboratory 4 tube lights. I need to have 6 tube lights to start with. So, okay, we have gone up to 4, that is okay for the moment. But what is important here is that the algorithms are completely different. But it's very difficult for me again. I have to start with a new algorithm. But let me just give you just 5 minutes. This is the overall scheme. Okay, it looks very bombastic, but it's not actually that bombastic. Technically, I have a 7-class problem. Similar to the previous situation, previously there was a 4-class problem. Similarly, I have to generate the data. Only thing is that in this particular problem, I am not using sparse representation. What Shoibal's thesis is mainly working for the collaborative robotics, developing algorithms using locality preserving projection, LPP. Has anybody heard the name LPP? Probably not. Okay. How many of you has heard the name PCA, LDA, principal component analysis, linear discriminant analysis? What are these algorithms for? Feature extraction. Basically for converting a high dimensional signal or image to a low dimensional signal or image, isn't it? Extracting features. But PCA and LDA, they work on, in case of images for example, on the global information available in the image. What LPP does, LPP actually works using the local information of the image. So there are some complicated, not complicated, mathematical algorithms. Every feature extraction algorithm, what does it do? Y is equal to W transpose X. Obtain W, either using PCA or FFT or LD or whatever it is. So obtaining W in LPP is a different algorithm. Okay, so from there we started, we modified the algorithms again. This will again take another 1 hour. So I am not going into the detail. If I go into detail, I will not be able to come out. In these algorithms, I generally behave like a human. So if I go inside, it's very difficult for me to come out. So I am not going into the detail of the algorithm. Problem I have mentioned, I will show you the result. Now see, but 2 minutes I have to say. That locality preserving projection, for that again, like that weight vector W that we calculated. Similarly, a weight vector has to be calculated in LPP also. The weight vector depends on what? From one image to another image, what is the distance? Distance means what? If an image is similar to another image, what will be the weight? You tell me, weight will be maximum. But if an image is completely different from another image, if you calculate the Euclidean distance, what will happen? That will be huge. That means the weight will be less. So those weights, how to calculate, that will become different in this particular algorithm. Look at the data set. Can you see what are, this appears Latin Hebrew, isn't it? But you can decipher from it like that. Can you see that this image is a little brighter compared to this image?
Yes.
This image is nothing but like the dictionary. But that is the dictionary under normal condition of images. Under normal condition, what will happen? Normal illuminating condition, intensity values are relatively high. Dark level 4, what will happen? Most of the illumination levels will be lower. Can you see that this dictionary color wise is much darker? So this is the dictionary for the normal condition. This is the dictionary for the dark level very high condition. So from there, what I want to show is like that. Look at the results. This one was our algorithm. We proposed this one. What is your conclusion from this column? What is your conclusion from the first column?
Normally, this is not that much.
Under normal condition, almost everything is working perfectly and almost everything is more than 99%. Actually, after 99%, who is 99.1 and who is 99.2, does it really make any difference apart from publishing papers? It does not serve any purpose. So, okay. But now see, if the dark level changes, what happens? When the dark level, just go to the dark level 4, can you see PCA, which is such a wonderful algorithm. Basic PCA is still very sophisticated and quite good. 99% came down to 32%. Look at the other algorithms, they are not that bad. Our performance also came down, but look at our performance compared to other algorithms. Significantly less degraded. Don't say good. Robust algorithms mean they are degraded but not that degraded. That is how we always are. Others are worse than us. Normally what do you argue? We are better than them. In robust, you will say that others are worse than us. Like that. So you can see with 32%, you will say how much difference is there. So this happens. Almost all algorithms that will come across, most of them, in challenging situations, they will find the weather very clumsy for them. This I can only explain if I go into the detail of the algorithm, and I am not gone into the algorithm detail. Okay, so and this fourth one I am not going into it. I knew that after 3 it will not be possible. So
Can I see the confusion matrix?
Can you see?
Yes.
0.64,
Yes.
0.62. Overall kota chilo around 71%. So if you take the average, it will come almost, because one is 0.58 and another one is 0.87. So it will come down like that. Is it okay? Understood? I am comparing the last one with that last column. You can compare the other paper. The paper is there, you can see something. So although this was there, I am not going into the again.
Which paper is that IOP paper?
This one was, yes,
Measurements
NST. NST is IoT paper, absolutely right. You are correct. And this one was, that was that physical script paper. Then after that, there is one more work in the IEEE Census Journal, but that again I have not included till now because that requires further discussion on rough sets, granular computations. So it will again, that will be a separate discussion. I will make that a separate. I did not include it here. I only wanted to explain the main intricacies of the problem here.
There is one paper I have seen in paper. One is that measurement, accurate analysis measurement.
Which one?
The sensor measurement and that robotic navigation.
If this is using vision, so there may be which one? The second one is that instrumentation measurement. This one maybe. I actually discussed about that shoe detection. Incidentally, because it is gesture. This lecture is on gesture. I discussed many things in remote world collaboration. In today's lecture, I did not include that because today's lecture title was gesture based. If I include that, then I cannot use that gesture based ones. That was the reason. Some other day, some other time we'll discuss.
This paper is also good, the chaos based data.
That is you have to judge. We are the authors. I cannot say this is good or not. So you investigate me a lot. It appears. That's good to know. I'll come because it's after all we are like messengers. We are actually the entire credit goes to Pritam, Shiva, and Devarshi for carrying out their work. They are the ones who have done the work. So I'll convey that people actually look into your work. I think I should stop here. Okay?
Sir, I have not very.
Just let me just, sorry, I can take the questions. So we have tried to show several configurations, and in response to his queries, I discussed a lot about human robot collaboration, as I mentioned, that this is, in my humble understanding, this will be a thing that will further prosper in next 20-30 years. Once that industry 5.0, 6.0 has taken off, this will further get from. So more and you will find more and more challenging problems. Something which I not discussed today, he brought that point, like human, it is basically leader-follower scheme, which I have not explained. Robot performs anticipatory movement with a human being. A human and a robot, they are lifting a chair or lifting a table. How that can take place? Say for example, the robot is helping you to lift the table, but the robot is holding the table like that, so you have to go like that. If you go like that, your hip joint, etc., ankle joint, they will go. So keeping the comfort and the safety of the human also is a very important factor in human-robot collaboration. So maybe some other day I will discuss that. I also discussed that point. The last algorithm, that was also very important one, because the last one was the first. I told you that human-robot handover gesture. If you remember, I want the object. I want the object is a static gesture. That I want the object. Now actually, what I will say, for example. Okay, I will not do it again. You can 15 minutes. So, say for example, the robot is helping me to screw a nut. Now, the object it is holding, the robot is holding, and I am screwing. What I will say, like a human, yeah, okay, you move it to the left, you move it to the right, further. The gesture is not static; it is dynamic. If the dynamically gesture changes, then that handover scheme will not work, isn't it? It is basically some static gesture which has to be identified. So in the context of the previous gesture, the robot has to understand how the object has to be moved, like this or like this or like this. Some other day, because the show must go on. Thank you. I hope you asked.
Yes, it feels within us a sense of great joy. My query is that all these mathematical. Okay, no problem. My query is that we are doing mathematically all these things within the computer, but in the robotic system, how we are taking the algorithm within the microcontroller itself, or it is being connected with the computer.
It is that robot is having the robot that we have shown. I told you that cursor resolution. That robot has a Raspberry Pi version 3 bus.
Okay.
I did not mention. I forgot. You will find in the other papers that you will find there is another small robot is there. Probably the optics paper is in that robot. That was.
What is small Kepler robot?
It is Kepler look like, but it is not Kepler. It is actually that one is also built by Professor Lakshmi. Okay, was built by him. That one had Raspberry Pi version 1 because that was built 5-6 years back. This one was built 7 years back probably. This one was built 5 years back. That one was having Raspberry Pi 3+. Now people can go for higher end processors also. But for our work, we have seen that it is
Raspberry Pi is good.
It's good enough for this kind of works. Good enough. We are not using that because our job is that we want to also show that with least amount of resources how you can perform your work. Because then the cost of the solution that you can propose, the cost of this particular robot finally if somebody makes it will not be more than 25,000 to 30,000. That kind of robot, if you go in market, you cannot procure it less than 3 lakhs, 4 lakhs like that. Okay. So our objective is that to make low-end solutions. Like Raspberry Pi 3 was found to be good enough for our work. No problem at all.
And for reason-based solution is this Raspberry Pi 3 and 4 is working very fine.
That good. But we already have this one is working okay. But of course I think the best. See.